Hello, my name is Kalechi Wana, and I'll be talking about, as well as give a demonstration as to how non-negative matrix factorization can be used for audio source separation, specifically musical audio. And I'll explain what the quotation marks around the source separation are. But before we get into that, just to describe what source separation is, just imagine you're at a performance, this jazz trio is performing. And all their instruments are playing at the same time. You have the trumpet, the saxophone, the bass. Basically, what source separation is taking this audio, right? All the instruments coming at you at once, and basically discerning which instruments are playing, right? And what they're playing, right? So you can have the bass doing its little bass line to do 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 do, something like that. And then the trumpet, belting something out, saxophone plays a nice riff, just separating those and isolating them out from each other, right? And we as humans can do this pretty easily. If you listen hard enough, you could hear what each of them are playing, but it's not that easy for a computer to do. So that's what all these source separation algorithms methods are trying to achieve. One of them that's kind of popular is called independent components analysis. And basically all that that's a really popular one, but I think the main drawback of that is that you need multiple recordings of the audio, and the only difference between them is how the sources are mixed, right? So you can have let's say in this situation, you could have a 30, 20, 50 split between trumpet, saxophone, bass, or a 60, 20, 20, or 40, 40, 40, 20, right? But they need to be different, and you need to have as many recordings as you need sources, right? So in this case, you would need 3 recordings, so that kind of gets unruly the more sources you have or require. So non-negative matrix factorization is another way that you can achieve source separation, but it's not the exact same kind of source separation as ICA, right? In terms that non-negative matrix factorization allows you to get, I guess, a finer or get a more specific breakdown of your audio signals, just based on how it works. So you have this original V matrix, which is just going to be a time frequency representation of your audio signal, and you're going to achieve that by using something called the short-term Fourier transform. Basically, each column represents a different frame of your audio. So this is frame 1, frame 2, frame 3, so on and so forth. And each row represents a different frequency. So this one right here, let's say it could be like 250 hertz or something, 500 hertz, 750 hertz, yada yada, so on and so forth, right? So you have this time frequency representation of your data. You could think of it like as a heat map. It's usually going to be a spectrogram. We'll discuss that later. And you're breaking this up into 2 separate matrices. So you have the W matrix and the H matrix. So the W matrix has columns that represent the different features. In this case, it'll just be the different columns would be the different frequencies that are most prevalent, I guess, in a signal. So let's say you have a signal that's just A's and B's, like the musical notes, right? A and B. So let's say column 1 here would just be the frequencies associated with an A, and then frequency 2, column 2 would be the frequencies associated with the B. So that's how those are activated. And then the H matrix has rows that basically play out how intensely those frequencies or these columns in W show up in the signal as a function of time. Yep. So yeah, it really just corresponds. The columns the columns of V corresponds to, I guess, these columns of H, and both those are time series, and then the rows of V correspond with the rows of W, in which those are frequency domain. All right, so the NMF algorithm, non-matrix non-negative matrix factorization algorithm seeks to reconstruct this that matrix, the V matrix, as a product of W and H. And to evaluate how accurate it is, you use this thing called the Kullback-Leibler divergence. All right, it's just formula right here. It's basically just like it's one of those, it's like a statistical measure of the difference between two distributions. And the algorithm is simple enough. You just initialize your matrices H and W, make sure that they're all non-negative, all right? And then you update H, update W, and then you just repeat steps 2 and 3. You just repeat updating them back and forth, alternating until you reach convergence. All right, and these are the update rules. They're developed by Lee and Sung in 1999, based on this Kullback-Leibler divergence. And you can see here that it's just you take the H matrix and then you do an element-wise multiplication of this product right here, transpose of V of a W multiplied by V divided by WH, blah, blah, blah. These fraction bars also indicate element-wise division, and this 1 is just the matrix of 1s, right? That has the same size as what was it? V, yeah. All right, and you do that same thing with W. You just follow that, and eventually it converges. Unfortunately, it doesn't give you the global minimum, so it doesn't give you the best possible solution. So that's something to look out for. You can give you a bunch of different solutions, so it's not exactly like guaranteed to find the best answer. All right. So these are basically just the steps to go through non-negative matrix factorization for audio signals. So first up, you have the short-term Fourier transform, and it's basically changing the audio data, which is just a stream of numbers, a list of numbers, I guess, an array of single dimension numbers into a complex valued matrix. All right. So again, it's just a spectrogram. So the spectrogram basically just tells you the intensities of different frequencies activated as a series of time. I'll show that later. But yeah, so you transform the stream of numbers, the audio signal, into a matrix. All right, using the short-term Fourier transform. Then you can do the non-negative matrix factorization. But first, you'd have to actually split up that complex value matrix into phase and magnitude, right? Because since it's complex, you can represent that as exponential form, phase, magnitude, all that good stuff. And because you're representing as that, you can look at the magnitude, and that's already non-negative, right? Since it's non-negative, you don't have to do any that already satisfies the criteria of non-negative matrix factorization. So you can just use that, all right? So you do N and F on the magnitude matrix. You just leave the phase matrix as it is. And then after that, you just filter. So you take the specific rows of the and columns of the W and H matrices, you just pick those out, and they use that to reconstruct a new matrix, right? So you combine those with the phase matrix that you just left aside, and then use the inverse short-term Fourier transform to recreate the time signal, and you'll get some isolated signals or isolated sources or whatever you want to reconstruct. All right. All right, so now I'm going to demonstrate what using non-negative matrix factorization actually looks like on an audio file and how all that works. All right, so first things first, just import, download all your dependencies. So you have the basic ones, NumPy, Matplotlib, but then you also have this one, Librosa. And Librosa is just really useful for managing audio files. So it allows you to load them into Python, read them into an array of values, and then also just manipulate them, like creating spectrograms. So we're going to do that later. So now we're actually going to download and see the audio file. So you have the sound. It says reference scale on C. So this is C major scale, right? And I'm actually just going to load that using librosa.load. That's a sample rate right here, and then this is the duration. But you'll see this is, yeah. Right. And I was able to play this using the IPD.audio, right? So that's what's used to actually create the playback. So the next step is to compute the short time Fourier transform. All right, so you have this thing called frame length and the hop length. Those are just parameters for the STFT. I'm not going to go into that right now. You can look into that. But what it does, you can use the librosa.ftft to actually create the to actually create this, right? So it's just a matrix. It's just going to be a matrix of complex numbers, and then separate them into magnitude and phase. So this is going to be the magnitude spectrogram. And this is how you visualize the spectrogram, right? So you have the time on the horizontal axis, frequency on the vertical axis, and then it's just a heat map to see which frequencies are excited as a function of time. You can see here that this is just an ascending scale. So you have do, 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 yeah, and so on and so forth, right? Yeah, these are all the frequencies. This is like the base fundamental frequency, and these are the overtones up here. And yeah, you do that with the phase. Just use mp.angle. Yeah, for the magnitude, you use absolute. So nothing wrong with that. And then you can actually get into non-negative matrix factorization. All right. So we already have a non-negative matrix in the magnitude, so we're using that. And then we add this tidy epsilon because some of the values are going to be zeros. And you don't want to be like dividing by 0. So you just add a tiny epsilon. I said 10 to the negative, no, yeah, 10 to the negative 10 here. So you just add that to the magnitude spectrogram, and then you get your dimensions. So this one is actually really important. So I is the numbers of sources that you want to extract. In this case, a scale only has like 8 distinct notes. So I just want to extract 8 notes. So this I would be 8. All right, so you do that, and then initialize the W and H matrices. Remember, make sure that they are non-negative as well. And then this is the actual update algorithm. It's fairly simple, just update H, then update W, and you do that for however many times you want. Usually it's 2 conversions, but you don't know when that's going to happen. So it might take too long. So I just said cap it off after repeating that 5,000 times. So do this. It actually takes some time, so I'll just cut to when it's done. All right, so it finished. That took around like, I guess, 1 or 2 minutes, right? But then you have this completed, you just completed the updates. So now you could actually plot to see what the frequencies and the activations are. So I'm gonna do that now. All right, so on the left here, you have the frequency spectrum or frequency spectra taken from the W matrix columns. And then you have the temporal activations from the rows of the H matrix, right? So you can see here on the left, yeah, frequency spectrum, yes. And then these are the activations. So let's see. Yep. So I think this is the interesting part, is actually filtering out the different sources, right? So there's 8 different sources, so to say. Basically, the sources for an NMF would just be the different sounds in the file. So not necessarily splitting them up by instrument. We only have one instrument here, the piano, but splitting them up by notes, right? So I would say these I sources are just the I different sounds created by, each instrument. So if you have like 20 instruments, that would be a lot of sources, right? Because they can play a lot of notes. But we could just, let's say we take source 0, 2 and 4 and 6, 0, 2, 4, 6, right? Let's put that in and we'll see what that creates with the sound. So I just take the columns and rows, whatever ones I wanted, and then you reconstruct the matrix by just multiplying them, right? And then combine that with the phase matrix by putting it in exponential form. So you take this magnitude matrix, the filtered magnitude, and then you multiply it by e to the, phase, e to the phase times I. All right, so you do that. This is a new sound that you get by using the inverse short time Fourier transform. All right, and then this is new audio. So it should sound different. What you should expect is to like have the scale, but some of the notes are missing, right? Because we extracted we only took in, I guess, only half the sources. So we should expect to see like half the notes missing. Yep. And then you can do this, different combination of them, right? So let's say 3, 7, let's do 5, right? So same thing. Right, and then if you put all of these together, 1, 2, 3, 4, 5, 6, and 7. Oh yeah, and also 0. My bad. Yep. It should be the whole thing. So we were able to see what non-negative matrix factorization could do for an audio file like a scale, right? Where the notes are played one after another, right? But what would happen if we had a file on which the sounds were, layered on top of one another? So I have this audio file now. This is called Sushi Box. It's just a track from a video game, Scott Pilgrim versus the World, the game. So I can just show you how that sounds like right now. I already loaded everything in. All right, so yeah, you heard that. And then what I want to do with this is get rid of that droning sound, that appears in the background, right? So let me see. Yeah, this thing, right? So I'm gonna try to get rid of that. I've already done everything. So this is what the spectrogram looks like. You can see it's much noisier, I guess, than the original, or much noisier than the scale. And yes, these are what the frequency spectrum or spectra and so on look like. Oh, a note, I changed this to 30, right? So since this has more sounds, I anticipate you need more, different sources to extract. So I put in 30. I guess a drawback of this would be you don't really know how many sources you need. If you underestimate it, you might not get a faithful separation or a good enough separation of the notes. And if you overdo it, not only does it take more time or resources, it also might just be, you might separate too much, right? So rather than, like, for example, this peak being this collection right here, you might be missing one that might show up in another source, right? You'd have to actually like combine sources to make one regular source, right? So I did 30, and since I already did this, I know that the sources that I want to extract or get rid of are the ones with these this, I guess, oscillating envelope, right? So you can see here, that'll be 0, 1, 2, 3, right? I think this one is number 8 or 11 or something. But you can see it's just like the humps going down, right? So if I do this, these are the sources that I want to get rid of. And these are the sources that, I should just comment out. These are the sources that I want to keep, right? So if I keep these sources, I should be able to hear the original file without the, that droning. This is what it sounds like. Hopefully it works. Oh yeah, yeah. Mm-hmm. All right. Okay, so you can see that it kind of worked, right? So you could hear that at some areas the that droning sound was flushed out. Other times it didn't work. But then an interesting thing is that also it kind of got rid of some unwanted. Well, it got rid of sounds that I didn't intend to, right? And that's just because frequencies are shared between different sources, right? So you could have like for example, a trumpet and a violin and a viola, right? They're two different instruments, but I guess they sound very similarly. So you might have sources or frequencies in the sources that mix together interfere. All right, so that's kind of an unwanted drawback of this. If you get rid of one source, you get rid of it, right? So you don't control what sources are playing at what time. Yeah, the computer doesn't discriminate. All right. So yeah, that's basically audio source separation using non-negative matrix factorization. I guess a follow-up to this would just be, rather than manually expecting this for the frequency spectrum, trying to find a way to group up these spectra to know which sources are like similar instruments and whatnot, similar sounds, right? Because I could tell that these sounds, these frequencies that have the oscillating bumps belong to the same group, but that's just by inspection. How could a computer do that? So probably some clustering algorithm to look at the frequency spectrum would work out. Yeah. And with that, I think that's it. All right. Thanks for watching the video. Mm-hmm.